Hi, I'm Jaeseo from POSTECH. Thanks for being here. The title of the talk is Formal Analysis of Networked PLC Controllers Interacting with Physical Environments. So what is PLC? A programmable logic controller, in short PLC, is an installable computer that logically controls systems in the industrial sites, such as airplane, ships, or conveyor belts. And they are widely used in the industry where errors can cause catastrophic damages. So by nature, PLCs are safety critical. Let's take a ship controller as an example. Imagine there are multiple ships navigating in the ocean. Through screws and keys and sensors, they interact with the physical environment like this. And they also communicate with each other so that they do not collide. And all these processes are administered by this control software. And we want to know if the ships are going to collide or not, or if the ships can reach their desired locations. Let's take another example of a chemical plant with two water tanks. They basically interchange water based on the user input. And the water exchange itself is governed by these ordinary differential equations involving the pipe sizes, pump powers, and gravity, and so on. And they also communicate, two tanks communicate with each other about whether they are going to send water or not. And if both tanks want to send water, they might as well just not send them and save some energy. So all of that, accepting input and reading the sensors and actuating and communication is encoded, is governed by this PLC program. And in this setting, we want to know that if a safety property, we can think of a safety property like tank 1's water level is always in between 20 or 80. And to analyze this system, we want to look at the system as a whole, not part by part, not just focusing on either of communication or program or physical dynamics, but one as a whole. To talk about the previous approaches of PLC semantics, for the software part, there have been many studies about PLC language semantics, and however, they are only confined in programming logic part, and in most of the work, they totally forget about other things like physical behavior and communication. For physical behavior, we have hybrid automata, but for hybrid automata, it is difficult to encode the programming environments and programming logic. PetriNet can nicely handle the communication, but also it is hard to encode the software and physical behavior. So, in short, part by part, each part of these are well addressed by previous approaches, but when we put them as a whole, one piece, we lack a method that can deal with the unified system. The key challenge here is how do we address the high complexity? As I elaborated, there are diverse aspects of PLC systems such as programming language, physical environment, and inter-PLC communication. And we want something that is expressive enough to cover all of them natively. And the price we pay for that high expressiveness is high complexity, and how to cope with this high complexity is our question. To sum up our goal, we want to develop a unified semantics of PLC system. We also want to develop a method for formal analysis such as model checking. And finally, we want to address the high complexity of our unified semantics. In short, we take object-oriented approach for modeling PLC systems. The PLC programming language semantics is covered by our K-based semantics, and the physical behavior is covered by the rewrite-based real-time semantics, and I'll talk about it in more detail in a minute. The system will be a set of PLC objects like these and communicating with each other. And the system is basically the set of these objects, and we want to apply partial order reduction, in short POR, on the whole system to deal with the high complexity. The issue here is to come up with a unified semantics that is suitable for POR. There are some hurdles to overcome for this goal. First, PLC communication is not suitable to be encoded as a single semantic rule. And as you can see here, there are a lot of stage diagrams for communicating behavior. They are specified in the international standards. There are multiple stages, and on top of message sending and receiving, and etc., there are more, such as flag settings and weightings and other things. Secondly, it is unclear how to apply POR on the continuous systems with continuously changing value like this, because POR is designed to reduce state space of the system that looks like this with discrete, explicit transition. To address these challenges, we have developed a unified semantics that is suitable for POR, exploiting the PLC-specific features. First, the multi-stage specification of communicating behavior is natively encoded by user-defined function blocks. Function block is something like a class and object in Java. And as you see here, communication, the multiple stages of communication is covered by the multiple lines of codes of the function block definition. Secondly, we have made explicit time jump transitions that can have arbitrary duration. From this state with clock value of 0, it could jump to a clock value of 2 milliseconds or 3 milliseconds or better. It could jump to a state with clock value of x, where x could be any value, could represent any value. So this is a brief sketch. So what is our unified semantics? As I briefly mentioned, we take an object-oriented approach, and where each PLC object has its own associated programs and programming environment and physical environment. And here's the class definition. And for the programming part, we use the K-based programming language semantics. K is a semantic framework where we can define executable operational semantics. And our whole approach, the whole approach is based on rewriting, and also K is based on rewriting, so they nicely come together. For the physical part, the key element of it is the tick rule, which describes the passage of time of arbitrary duration. For example, when the temperature, this graph depicts the continuous change of the temperature value, and from this state with the temperature of 33, after X milliseconds, the temperature value is updated to this value according to the flow function and the PLC object. For communication, we define another class called connection so that PLCs can exchange messages through the buffer of connections. And what to do here is to write semantic rules that revolve around this object class. For the core behavior of the communication, we have identified and defined atomic operations for communication. So here is a function block definition for connection establishment, and there are two atomic operations for communication: connect request and is connected. And this rule describes the connect request rule, where it consumes the connect request statement and flips the the validity value from false to true. So that was our the big picture of the unified semantics. Now let me talk about the formal analysis. Formal analysis, such as model checking, is possible with our unified semantics because they are executable. Note that our semantics is symbolic. That means we can have a symbolic state that can represent infinite number of concrete state. And for example, here we have a symbolic state with an SMT variable x that represents the temperature. It can represent an infinite number of PLC objects that with any temperature values. What is better here is that the duration of the time jump can also be symbolic. So given another SMT variable t, we can describe a passage of time t milliseconds. From this symbolic state, we have this symbolic state where the timer value is reduced by t and the temperature value is updated according to the flow function. We have implemented our unified semantics with mode rewriting engine, and we can perform model checking by formulating a search command. The model checking problem is from this initial state, which can be symbolic, is an error state reachable with our unified semantics. So here is the part where we specify the initial state, and here we have two SMT variables A and B. And this is the search command that performs the model checking. And here specifically, the condition looks for a state that has water level outside of the desired range. Now to address the high complexity of the semantics, we apply partial order reduction, POR. POR is a technique that is developed to fight state explosion. And the idea of it is when there are many execution paths possible, but if they converge into one and if they are essentially not different, we don't want to explore all of the possibilities. We just want to explore one of them. We applied POR using ample set approach, and an ample set is a subset of enabled set which holds the transitions that are enough to capture all the behavior, all the important behavior. For example, in this diagram, we have three choices: executing this statement, executing this statement, or executing this statement. And let's say x and y are local variables, and since they are local, it is not the order of the assignment execution of either of these are not so important, so we can just explore one of the paths, which is taking this PLC1's assignment statement, and then that way we can reduce the state space. So we have fabricated the ample set definition so that the some group of transitions take precedence over other groups of transitions, such as if start rule is enabled, it is the ample set. If it is not enabled, then internal rules such as assignments are the ample set. If they are not enabled as well, then communication rules can be ample set, and so on. To evaluate the effectiveness and efficiency of our approach, we first need to come up with benchmark models. And we have adopted some of the standard hybrid automata benchmark models, such as water tanks, railed vehicles, networked thermostat, and etc. Because theoretically, hybrid automata can encode the whole PLC system, but not practically. We have developed a model for SWOT, a secure water treatment. It's a well-known model. It's the closest one to the real-world example, and to our knowledge, it is the first time to come up with a SWOT model that is available for formal analysis. Models in mode were much more affordable because PLC programs themselves can be a part of the model. That is because we have the executable semantics of PLC programs. We only need to specify the object settings and flow functions. But for SpaceX, a hybrid automata solver, we need to encode the PLC program behavior to hybrid automata. Basically, we want to convert this thing into this thing, and it's manual and it's impractical, and in the end we have to simplify a bit to construct hybrid automata for evaluation. Here is the comparison between our approach with mode and SpaceX. And the x-axis represents the increasing time bound of the analysis, and y-axis is the time taken for the full space exploration. And SpaceX takes exponentially more time as the time bound grows, but for mode it becomes relatively low, and in some of the cases it's almost instant. And here's the comparison of analysis time with and without partial order reduction. For models with communication, in these 4 graphs, analysis were basically intractable without partial order reduction, but it was feasible with POR, and this shows that our POR method was effective. To wrap up, here is our contribution. We developed a unified formal semantics of PLC program that is suitable for effective POR, and then the implementation and evaluation of the proposed unified semantics. And we believe that we take a step closer to verifying properties of real factories out there. In the future, we plan to extend our semantics to support more complex PLC features such as multitasking, and further optimizing the state space reduction techniques, and we ultimately want to integrate our approach into existing PLC verification tools. That's it for today. Thanks for listening.
Do we have questions from the audience? May I start with the first question? So you use the SMT solver for the solving the tasks. But then the experience is that, you know, if you have integer domain, you can fairly trust the SMT. But then if you have something beyond linear or integer domain, then you feel like, oh, cautious. Maybe they'll give me wrong answers. But then the data sits in models environment, so I would think that it's likely to be non-integer. Right? So do you have difficulties with dealing with SMT solvers? As in the return value, is that always reliable?
It was always set or unset, basically.
So you never found any bugs that unstable?
That SMT solver
yes.
caused by an SMT solver?
Yes.
We didn't face that.
You didn't face that. Okay. Right. Okay. You also mentioned that the next step is to extend it to the industrial size or more complex usage of the controllers, right? So can you, as an outsider, can you tell me more about the size of the industrial size and the size of the experiments you have now, and what's the gap?
Well, what I've seen from the internet, the real-world factories will have 10,000s of codes, and which is a lot. But well, at this moment, like our benchmark models are relatively much smaller than that.
More? Okay.
Yeah.
I see. So maybe by extending to the industrial size, you will need more of the partial order reduction there.
Probably. Yeah,
all right. If we don't have any more big questions, we can thank our speaker again.